Let's continue on with the idea of light rather than being simply a wave if it has more particle-like properties. So this idea is, okay, we're going to have light coming in, and the light should come along and it'll have some certain frequency, it'll have a certain wavelength. It can hit this electron, and it would then possibly move the electron around perhaps, but it's also possible that the light comes off the electron. And basically, well, can't we just treat this like a collision? We've already talked about how light could have momentum. It's something that shows up in special relativity. It's even something that shows up from Maxwell's equations. So if we try treating light as if it were a particle and hitting some other particle, we could just do this with simple momentum conservation. So we can imagine light coming in, and it bounces off at some angle theta. And if we were to do that, we could then talk about, all right, it bounces off, its momentum should change, and since there's this relationship between the energy of a photon, or energy of light, and its momentum in the following form, the momentum divided by speed of light, then we can talk about, okay, the momentum will change, the energy will change, and since the energy of a photon is related to Planck's constant and the frequency of that light, also in the same way it would have a relationship to the wavelength of that light, in the following way, we can talk about how the wavelength changes. So we can talk about the initial wavelength coming in and the wavelength then coming out. So lambda naught and then lambda prime. And if we are careful with our derivation doing conservation of energy, conservation of momentum with collisions, this is the form we'll get, that the difference between the two wavelengths, the initial and final, is going to equal Planck's constant divided by the mass of the electron times speed of light, multiplied by 1 minus cosine of theta. So the more of an angle this thing gets bounced off at, the greater we're going to see then the effects of the wavelength shift. And of course, if there were nothing there, it would just go straight through and there'd be no shift to the light at all. So this is the sort of thing you would expect, like I say, from basically ultimately the collision of particles, the collision of balls together, and you talk about the energy momentum change before and after the collision, and this is the sort of effect you get. We could also do this with different particles. If this were a proton instead of an electron, only change that would happen is you would put a different mass here. Now, how is this supposed to have differed from simply the standard electromagnetic theory? Well, remember, if the photon, if light is supposed to be this wave and it's ultimately an oscillating electric and magnetic field, then as this wave is moving along, it's an oscillating electric field, and the electron then is going to be pushed around by that electric field. The magnetic field, since the electron is initially not moving, we wouldn't expect a force there. So the electron is going to be shifted up and down by this incident light wave coming along. Plus the energy should also be pushing the electron along the direction that the light is coming from. So we're expecting the electron to be pushed forward and oscillate up and down due to the oscillating electric field. Now, if we're imagining the electron is moving forward now, and it's also oscillating up and down, when it oscillates, it's actually going to then produce its own oscillating electric field, and so it would actually emit light. And since it's also moving forward, there's then a changing velocity to the electron, which also means it's going to actually experience a Doppler shift from the light. The faster the electron is moving along, the greater that Doppler shift is going to be, and so there's going to actually then be a changing wavelength, or a changing frequency to the electron as it oscillates up and down, because the incident light appears to be changing because of that Doppler shift. Faster the electron goes, the greater the Doppler shift, which also means how the electron oscillates up and down will change. So the expectation is that you're going to basically see the electrons get sped up, and they're going to not just shoot off one frequency of light, but it's going to emit a spectrum of light, basically a distribution of light. That's what was originally expected, but the experiment showed that instead of getting that sort of spectrum, there's really just one dominant frequency of light bouncing off the electrons. This was done originally with X-rays, since that's usually the easiest to do these sorts of experiments with, for reasons I can't get into for now. But this was, again, unexpected on the wave theory, but if we treat light as if it were some particle-like thing hitting an electron and just dealt with momentum conservation, we get the effect we want, and this was the really convincing sort of experiment that made people say, yeah, this quantum theory, it's got some legs to stand on.